Welcome back to our study of the fundamentals of operating systems based on the textbook Operating System Concepts, 10th edition by Abraham Silberschatz, Greg Gagne, and Peter Galvin. We're beginning lesson 2 in our study of the process management system of the operating system. So let's pick up where we left off. You may recall that the current state must be stored until the process regains the central processing unit. Each process is represented in the operating system by a process control block. It's abbreviated PCB. It's also called a task control block. A PCB is shown in this image. It contains many pieces of information associated with a specific process, including these. The process state. Now that state may be new or ready or running or waiting or halted, so on. But whatever the process state, that has to be recorded. The program counter. This is a counter that indicates the address of the next instruction to be executed. I remember telling you earlier that when an instruction is loaded into the memory, that along with it comes the address of the next instruction that needs to be run. That's what's stored in this program counter. There are also CPU registers. The registers vary in number and in type depending upon the computer architecture. They include things like accumulators, index registers, stack pointers, and general purpose registers. Along with the program counter, this state information must also be saved when an interrupt occurs. It allows the process to be continued correctly afterward when it is rescheduled to run. There's also CPU scheduling information. This is information that includes a process priority or pointers to other queues or other types of items. There's also memory management information. This is information that includes such things like the value of the base register where this process starts and the value of the limit registers or the bounds registers, various page tables and segment tables, things like that, depending upon the memory system used by the operating system. There's also accounting information. This is information that includes the amount of CPU time and real time used, time limits, account numbers, job or process numbers, and so on. There's also an input-output status. This is information about the list of I/O devices allocated to the process or the list of open files that are being used by the process. In brief, the process control block simply serves as a repository of all the data needed to start or restart a process, along with some accounting data. Think about that simple example I just gave you. This image shows what happens when a process loses the CPU. This is called a context switch. That is the process state being saved for the job exiting the CPU and the process state of the next job being loaded. That's a context switch. And context switches take time. We'll have to keep that in mind. You see on the left, job 0 losing the CPU, and on the right, job 1 is gaining the CPU. Or should I say process 0 and process 1. You see how process 0 is idle while process 1 has the CPU? It's sitting in a ready queue until it gets another round with that processor. Actually, it may not be idle. Remember, it could have voluntarily given up the CPU to use another device, so it may have gone to some waiting queue. Nevertheless, unless it gave up the CPU because it was finished, it'll be back. We'll talk more about that very soon. The process model discussed so far has implied that a process is a program in execution that performs a single thread of execution. For example, when a process is running a word processor program, a single thread of instructions is being executed. This single thread of control allows the process to perform only one task at a time. Therefore, the user can't simultaneously type in characters and run the spell checker. Most modern operating systems have extended the process concept to allow a process to have multiple threads of execution and therefore to perform more than one task at a time. This feature is especially beneficial on multi-core systems where multiple threads can run in parallel. A multi-threaded word processor could, for example, assign one thread to manage the user's input while another thread it runs the spell checker. Surely you've noticed how your own word processing software flags misspelled words with a squiggly line or even changes the word for you. Don't you hate it when Siri does that? She's not always right. On systems that support threads, the process control block is expanded to include information about each thread. Other changes throughout the system are also needed to support threads. We'll talk more about threads in another unit. The objective of multi-programming is to have some process running all the time, so as to maximize CPU utilization. According to Merriam-Webster, the definition of multi-programming is the technique of utilizing several programs concurrently on a single computer system via multiprocessing. The objective of time sharing is to switch the CPU core among processes so fast that users can interact with each program while it's running. Time sharing simply refers to the technique that allows a process to use the CPU for some piece of time, a time slice, so to speak. The word time quantum is also used for that slice of time. To meet these objectives, the process scheduler selects an available process for program execution on the core. The process scheduler has two assistants, the job scheduler and the CPU scheduler. The job scheduler is responsible for bringing jobs from secondary storage and place them in the ready queue for processing. We're going to find out shortly that there's another job it has of taking jobs out of the system when it becomes bogged down or slowed, but we'll get to that later. The CPU scheduler is responsible for selecting which process gets the CPU next. In other words, it's the scheduler responsible for moving those processes between all those queues. Your professor may refer to the job scheduler as the long-term scheduler and the CPU scheduler as the short-term scheduler. Those two terms are used quite often in our field. Each CPU core can run one process at a time, remember? For a system with a single CPU core, there will never be more than one process running at a time, whereas a multi-core system can run multiple processes at one time. If there are more processes than cores, excess processes will have to wait their turn until the core is free and be rescheduled. The number of processes currently in memory is known as the degree of multiprogramming. Balancing the objectives of multiprogramming and time sharing also requires taking the general behavior of a process into account. In general, most processes can be described as either I/O bound or CPU bound. An I/O bound process is one that spends more of its time doing input-output than it spends doing computations. A CPU bound process, in contrast, generates input-output requests very infrequently, using more of its time doing computation. These are the guys that want to hog the CPU. And one of the tasks of the job scheduler that we talked about a moment ago is to try and pick out a mix of CPU-bound and I/O-bound jobs to load. As processes enter the system, they are put in a ready queue where they are ready and waiting to execute on the CPU's core. This queue is generally stored as a linked list. A ready queue header contains pointers to the first process control block in the list, and each process control block includes a pointer field that points to the next process control block in the ready queue. The system also includes other queues we talked about. When a process is allocated to the CPU core, it executes a while and eventually terminates, or is interrupted, or it's waiting for the occurrence of some events like an I/O. Suppose that a process makes an input-output request to a disk. Such devices run significantly slower than processors. The process will have to wait for the I/O device to become available. Processes that are waiting for a certain event to occur, such as the completion of an I/O, are placed in the wait queue. A new process is initially put in the ready queue. It waits there until it's selected for execution or is dispatched. Once the process is allocated a CPU core and is executing, one of several things can occur. The process can issue an input-output request and then be placed in an I/O wait queue. The process could create a new child process and be placed in a wait queue while it waits for the child's termination. The process could be removed forcibly from the core as a result of an interrupt or having its time slice expire and be put back in the ready queue. Remember, in a time-sharing system, access to the CPU is allocated by chunks of time. These are referred to as time slices or time quantums. In the first two cases, the process eventually switches from the wait queue to the ready state and is then put back in the ready queue. A process continues this cycle until it terminates, at which time it's removed from all queues and its process control block and resources deallocated. You remember in our earlier unit, we said that parts of the responsibilities of the operating system are to allocate resources, monitor resources, and deallocate resources. Okay, you're hearing how it's done. A process migrates among the ready queue and various wait queues throughout its lifetime. The role of the CPU scheduler is to select from among the processes that are in the ready queue and allocate a CPU core to one of them. The CPU scheduler must select a new process for the CPU frequently. An I/O-bound process may execute only for a few milliseconds before issuing an I/O request. Although a CPU-bound process will require the CPU for longer durations, the scheduler is not likely to grant the core to a process for an extended period. Instead, it is likely designed to forcibly remove the CPU from the process after some amount of time and schedule another process to run. Therefore, the CPU scheduler executes at least once every 100 milliseconds, although typically much more frequently. Sometimes it becomes evident that there are too many processes in the system, which I just mentioned to you, probably because of unexpected decline in performance. Some operating systems have an intermediate form of scheduling known as swapping, whose key idea is that it can be helpful to remove a process from memory to reduce the degree of multiprogramming. I hinted at all this in the last few minutes. This is performed by another assistant manager to the process manager. It's the mid-level scheduler. I was mistaken, wasn't I, when I said it was a job scheduler that did that. This is another one, mid-level scheduler. Later, the process can be reintroduced into memory and its execution can continue where it left off. This scheme is known as swapping because a process can be swapped out from memory to the disk where its current status is saved, and later swapped back in from the disk back to memory where the status is restored. Swapping is typically only necessary when memory has been overcommitted and must be freed up. You can see from this graphic at the bottom of your screen how it's swapped in and out as necessary and placed in the ready queue. As mentioned earlier, interrupts cause the operating system to change a CPU core from its current task and to run a kernel routine, or as we mentioned earlier, change from a user program to a system program. Such operations happen frequently on general-purpose systems. When an interrupt occurs, the system needs to save the current context of the process running on the CPU core so that it can restore that context when its processing is done, essentially suspending the process and then resuming it. The context is represented in the process control block of the process. It includes the value of the CPU registers, the state, various memory management information like we discussed earlier. Well, I think this was a good lesson. Why don't we take a break right here, look over your notes, take care of any business that you have to take care of, and when you're ready, come on back and we'll begin lesson 3 on the process management system of the operating system. We will pick up on context switches in this next lesson.